Hello and welcome to another tutorial. I'm going to continue our discussion on creating a simple hello world and compiling it to native executable binary. We saw this already on the macOS platform and Linux platform, and I said that in your Linux, if you cannot compile, you probably are missing one of the one or more dependencies. So you can look at the output, what output or error native image tool creates. Right here, for example, I ran it and it tells me that it appears that libz.a is missing, and then you search to Google and install the zlib1g-dev for compilation. We looked at the output stages both in the Mac, like all the details, and in this lecture I'm going to go into more details, what this means, just a brief introduction. We don't need to really be concerned that much with what this means. Eventually, if the compilation succeeds, we get the executable binary. But before that, let's also try to recap quickly how this native compilation works by creating a quick hello world application in Java, and then using the GraalVM native image on the Windows platform to compile it to native executable binary. So install native image, you download basically GraalVM, and then use the Graal updater or the GU. In Windows it's the shell script, so you have to use gu.cmd, and then you have to install Microsoft Visual Studio Community Edition. Native image on Windows only recognizes the default Windows platform toolchain, which is MSVC or Microsoft Visual Compiler, and then you have to run this script, shell script, vcvar64.bat, which I already showed you where you can find it. You go into the build in the MSVC community and then build auxiliary, and then run this script. This sets up the correct environment variables for your shell or the command prompt, so that it can know it can find the cl.exe, which is the command line tool for calling the MSVC compiler, and native image relies on finding that cl.exe so that it can compile to native executable binary. And I also told you that the easiest way is to actually create an environment variable, a global environment variable, and then basically so that when you just type it and execute it, it executes this shell in terminal. So compile hello world.java with Java C. You can use JDK 17 or the Java C that comes with the GraalVM 17, and run native image.cmd. So know that this is a command line script. This is not a native executable file. Unlike Linux and macOS, where the native image is actually an executable, on Windows it's just a command line script on the class file. So again, native image, we always run it on the class file. So let's head to Windows and quickly do this. So here's my Windows. I have created this test directory on my desktop, and I am going to so my virtual machine is running a little bit slow, but what I'm going to do, I'm going to open up a CMD or command prompt, the simple command prompt in Windows, and then I'm going to create a Java file, hello world, and then just print the hello world to the console. So we're going to here right click, new, let's create a text file and then rename it to something hello world.java. All right, my virtual machine freezes a little bit. So right click, new, and then a text document, and then we want to rename this to hello world.java. Okay, and after that I'm going to quickly open it up and then run the create a class, and then we're going to compile it, and then we're going to so yes, let's change the extension, and then right click. I'm going to open it with a text editor. On Windows, I prefer to use Notepad++. Now, obviously, in the future lectures, I will switch to the Eclipse IDE, and we will see actually how to set up the external tool in Eclipse IDE so that it can automatically call the native image tool. Now, if you're not familiar with the concept of external tool in Eclipse IDE, I will go into the details so you understand the meaning of the external tools that the Eclipse provides. So let's open it up with the external, basically with the Notepad++. All right, so we're going to say that public class hello world. All right, just the routine, and then public static void main. That's the entry point to our Java application, string args. And then in the main method, we're just going to say that system.out.println hello world from C++. Hello world from C++ in Java. And then exclamation marks and then semicolon. We're going to save this. Yes, we want to save this. And then obviously the first thing that we do, we compile and then we run our Java application on the JVM to make sure that there is no error, there is nothing, and after that we just compile to native executable binary. So my recommendation is that always check your Java application, run it on the JVM to make sure everything works fine, and after that at the final stage compile it to the native executable binary. So let's change our directory to this test directory on the desktop. We're just going to drag and drop. And then we have this hello world Java, and then I'm going to say Java -- version. And we're using OpenJDK 11 from Microsoft. So did we define the Graal home? Yes. And then we also on Windows, I also defined the Graal bin directory, right? So, and we said that in order to use this, unfortunately, this program files has a space in it. So we kind of need to put this in double quotes, this Graal bin, and then for / Java -- version. Now we shouldn't basically echo it. So this one. So OpenJDK 17. So we're going to also use Java C, and then we're going to say hello world.java, right? So we're going to compile this, and it's going to create the class file and put it there, right? Done. And now we're going to launch this, our Java application, which is the class file on the JVM, right? Because it's much easier. So we're going to say Graal bin instead of Java C, just Java. And then we don't need to specify the class path, or we just tell it this current directory. And then we're going to tell it hello world. And then we don't use the dot class, right? And hello world from C++ in Java. So everything works fine. Now, if I want to finally compile to the native executable binary, I need to call the native image. But if I just call the native image now on this class file, it's going to fail, because if I look at my path environment variable, at the moment it doesn't have any of the MSVC or Microsoft Visual Compiler, right? Microsoft Visual Studio is not added to the path environment variable, which means if I say cl.exe -- version, it's going to say that I cannot find cl.exe. All right, that's because it's not added to the path environment variable yet. So the command prompt or terminal, it cannot find it. So what should we do? If you recall in the environment variables, so in any terminal, if you type env and hit enter, all right, let's one more time, it tells you which environment variables, which global environment variables are defined for your terminal, right? In Mac OS, Windows, Linux, doesn't matter. This env works. And then if you recall, we defined a MSVC vars, right? We defined this environment variable, global environment variable for the operating system, and it's pointing to the vcvars 64.bat. And this is a shell script, so we can just execute it, right? MSVC _ vars. So if I type it and hit enter, it's equivalent to typing this full path to this and let's see if the space works fine or not. No, so we have to put it in double quotes so that the space in program files doesn't. So now this executes and then it sets up the Microsoft Visual Studio 2020 Developer Edition, and it's appends on all the required directory to the path environment variable, and it tells us that, hey, I set it up for the 64-bit compilation, which is the correct. I want 64-bit compilation instead of 32-bit. Now if I clear and look at my path environment variable again, and you see that now there are a lot of directories that from MSVC, Microsoft Visual Studio, that has been appended to the path, right? Lots of directories. That's why I recommend instead of trying to manually add these directories to the path, just define that global environment variable MSVC vars that points to the right shell script that comes with the Microsoft Visual Studio, and just execute this environment variable each time, right? So this works. And now that it's set up, if I say cl.exe, for example, -- version, the terminal is able to find the right tool, right? This CL, which is the command line interface for the calling the MSVC compiler. And now I'm ready to call the native image on this class file. So again, double quotes, and then use our global environment variable Graal bin directory, right? And then / I believe / might also work on Windows, but here I'm using / native image .cmd. It's a command line script, and then we're going to tell it -cp here, and then hello world, and we don't specify the name, and we can specify the name of the output file, let's say my app, and then hit enter. It is going to take a little bit of time because I'm running it on a virtual machine, but hopefully this will finish up and we will get a native executable. And we've seen in the past that the executable is already like 10-11 megabytes, whereas our class file is just like 1 kilobyte. And the main reason obviously is that it has to compile a JVM, add a garbage collector, and then compile all the class files from the JDK, so they all basically require some space, 10 megabytes or so. So this is still doing some stuff. Let's see if this is going to work. Still waiting a little bit, trying to so the first thing that it will output is the version, which version of GraalVM we're using. So I'm going to let this to run, and then let's head back to our PowerPoints. So you write your class files, and then you run the native image cmd, and then run it on the class file that has the main method, and then it goes ahead and compiles, and eventually you get a hello world.exe. And we said that in macOS and Linux, the executable files don't have any extension. On Windows, they have .exe extension. And you see here, it's like 11, 12 megabytes, which is very large. Whereas your class file was only 1 kilobyte, right? So this executable file not only has your Java application, it has a lot of stuff like a garbage collector, a JVM, all the class files. Now let's quickly go through the build stages, which is all the informations that the native image tool prints to the terminal in the process of compiling your Java application. And here's the documentation. So it's just GraalVM, the version, and then reference -manual, and then the native image tool, and then the build output. So you can go, let me just quickly open this up in a browser. And then you will see that we can, basically the material that I'm writing here, more or less a concise version of what's on the reference manual. In the future lectures, I will walk you through all the actual official documentation of the native image on the GraalVM website, but for now I just wrote a concise or very brief basically explanation of what happens here. It also has an example that what's going on, and then it walks you through all the stages, right? So first of all, the first stage is initialization. Let's look at the Linux output. It just tells you GraalVM native image generating hello world. So nothing went wrong. The native tool was able to execute, right? So that's the first stage, initialization. In this stage, the native image build process is set up and features are initialized. And version info, user provided features, right? Version info is basically here in the initialization. Version info GraalVM 22 something. We saw that in the most recent version, they also print which GC is being used and which default tool chain is being used, right? The version info of the native image process, this string is also used for the Java VM version. So we saw that there are system properties that JVM uses, and when you compile to the native executable binary, you can still access these system properties using the system class, right? System.getProperty Java VM version within the generated image. User provided features. These are the extra system properties, right? All features that are provided by the user or implicitly registered for the user. For example, by framework. GraalVM native image deploys a number of internal features which are excluded from this list. All right, and then the next step is performing analysis. So performing analysis. In this stage, a points to analysis is performed, which means the compiler chases all the pointers on the stack, right? All the references to see which objects they're pointing to in the Java heap. The progress indicator visualizes the number of analysis iterations. You see these stars, these are progress indicators, right? So each star means one round of iteration. Okay, so the progress indicator visualizes the number of analysis iterations. A large number of iterations can indicate problems in the analysis likely caused by misconfiguration or a misbehaving feature. Now, performing analysis has to analyze a couple of different things. One is reachable classes, fields, and methods. What this means is that if there are some classes in your application that your main method, right, doesn't really rely on them, doesn't call them, doesn't use them, and none of the classes that are used or the types that are used in main method, they don't really use some of the classes, then those classes are not reachable and they're not going to be compiled, because the compiler of the native image is smart enough to know that the entirety of your Java application doesn't really depend on them. Remember that we're doing a static compilation, so the compiler at the compile time has to chase all the pointers, all the types, figure out all the dependencies to eventually figure out which classes are reachable and they have to be compiled, or which classes are not reachable, they have no effect on your application. Reflection registrations, right? If you're using reflection API, JNI access registrations, if some of the methods in your classes are native methods. We already know that most of the JDK classes have, at least the classes that are in the core Java lang package, they have JNI access, right? They have native methods and runtime compiled method, right? So these are the things. And if you look at here, it tells you, for example, in this output, 3,251 classes reachable. So your Java application depends on 3,251 classes to be run. Obviously, you didn't write 3,000 classes in your Java application. We just wrote a simple hello world class, but the rest are the JDK dependencies. 5,529 fields reachable and 16,881 methods reachable, and then 28 classes, 0 fields, and 173 methods registered for reflection, 57 classes, 58 fields, and 51 methods registered for JNI access, which means of all the dependencies of your Java application, there are 51 native methods that have to be registered and compiled, and the compiler has to figure them out in order for your Java application to successfully run, right? So these are more like statistics, what's going on. And after that, building universe. This is where we start putting all these information together and start compiling. In this stage, a universe with all classes, fields, and methods is built, which is then used to create the native image. Parsing methods, right? Parsing methods means in this stage, the Graal compiler, the native image compiler, parses all reachable methods Parsing just means it tokenizes them in a way that the compiler understands them, and then because method means it's source file, right? Or basically the class file. These are the way that JVM understands. But now the compiler needs to compile them into native executable instructions for the CPU. The progress indicator is printed periodically at an increasing interval. And again, those stars are showing you how long it's going to take to finish up this method. Okay, and then inlining methods. And I've mentioned this before. Inlining is a common technique that the compilers use to save some time for calling methods, right, or functions. Usually what happens here is that whenever you call a method or function, in the actual file, compiled file, which is basically assembly instructions for the CPU, it says go to this memory address, and then basically a function is just a pointer, right? It's an address in memory. The CPU jumps to memory address and then loads all the instructions. All the lines of the code in a function or method are stored somewhere, and that block of memory has an address, which is the method or function, which points to it, right? And inlining means the compiler copies all that code in the actual main method, so or whatever other functions that is calling your method. Therefore, there is no jumping from one address to another to load the extra instructions. And compilers nowadays are very smart about this. So in this stage, trivial method inlining is performed. The progress indicator visualizes the number of inlining iterations, right? Now we know that the Java compiler, Java C, is a very dumb compiler, which means it rarely uses any inlining. Now Java C is good for example, if you have a public static final field, it just replaced all those basically fields with the actual value, but Java C doesn't really do any optimization in terms of inlining. So it's mainly the GraalVM compiler that does all these static analysis. So inlining methods, you see this stage has 4 stars, which means actually there's quite some time and effort for the compiler to inline this a lot of methods. Build stages, compiling methods. So after we inline, now we go ahead and do the compilation. In this stage, the Graal compiler compiles all reachable methods to machine code. Now again, it's smart about it, and the reachable is the keyword here. Now a class might have a lot of methods, but your application might not use some of those methods, right? They're just there, but they're not usable. So the Graal compiler doesn't compile those methods to native binaries because they don't have any effect on your application. They are never used. Whereas in the JVM, like the class file already includes the bytecodes for those methods, but the Graal compiler realizes that some of the methods are never used or called in your application, so there is no point of compiling them. So it's smart about it, and it means it's doing optimization. And previously we saw that there is an optimization flag that you can pass to the native image compiler, so you can turn the optimization off, but then most likely the size of your native image becomes larger because it's not smart about selectively compiling method. It just compiles everything. The progress indicator is printed periodically at an increasing interval, and you see there is like 4 star here, which means it also takes time and effort for the compiler to finish this phase, compiling methods. And then creating image. Finally, once everything is done, we know that just like C++ application, after compilation there is a linking phase, and it's the linker that puts all the compiled files together, right, and creates one native executable. Same here, there is a linking phase that happens that puts all the compilations together. In this stage, the native image is created and returned to disk. Debug info is also generated as part of this stage. And what is this debug info? Here it says, gives you some information of what's the total size of the native image. Here 11.96 megabyte, and it gives you a kind of a brief breakdown of which parts of this, so what constitutes this total 11.96 megabyte. It tells you that almost 4 megabyte is for the code area, which consists the binary code of 7,383 compilation unit, just like C++, that each CPP file is called a compilation unit. Here, most likely each class file is called a compilation unit. Almost 7 megabyte for image heap. just this is similar to Java heap. Even when you launch the JVM, there is a heap or memory area that it stores information. 1,634 classes and 90,000 objects, right? Objects are stored on the heap, and on the stack they have pointers to those objects. 1 megabyte for other data, just like JVM has meta information, meta space that stores static fields or like the class informations for reflection. It also has to allocate some space for that. And so this gives us a breakdown of what's going on. So code area, the code area contains machine code produced by the Graal compiler for all reachable methods, right? Again, the compiler is smart about which methods to compile and which to not include in the final binary. If you have turned on the optimization, which is already turned on by default, right? Therefore, reducing the number of reachable methods also reduces the size of the code area. Makes sense. Image heap. So again, code area means the machine code or the assembly code, right? For the methods, each method, the code that is inside each method gets translated into instructions, right? Assembly instructions or machine code. Now, obviously, besides that, you need the Java heap, right? A memory that basically the objects, the state of the objects are stored. So image heap mimics basically the Java heap when you launch your application on a JVM. Image heap contains reachable objects. These are the state or the data that object is stored, right? Such as static data, classes initialized at runtime, like static fields, and byte array for different purposes. Now we have general heap data stored, byte array, similar with JVM, right? There's a byte array that stores data. Graph encodings stored in byte array. Method metadata stored in byte array. I mean, metadata just means some stuff, extra stuff in the class files. Each object has a class file associated with it. What this means is that each object or each class has some meta information, right? So finally, if you have enabled the debug information for the native image compiler, it also shows the debug information, and you see there is also some other data here. So other data means the amount of data in the image that is neither in the code area, which means the instructions, machine assembly codes for the methods, nor in the image heap, object data, nor debug information. And we know that same with the C++ compilers, you can compile in the debug mode or release mode, which means if you compile in the debug mode, the binary file has extra information for debugging purposes. By default, if you turn on the optimization for the native image compiler, you don't get any debug information. This data typically contains internal information for native image and should not be dominating. So here it says that 1 megabyte was for other data. All right, so finally, resource usage statistics. So this line, this section, and also the GCs, peak RSS, and CPU load. It just tells you more information. It doesn't really, it's not directly related to the application, Java application. It just tells you what happened, how much CPU load was during the compilation, how much memory was used. Garbage collections, the total time spent in all garbage collectors, total GC time divided by the total process time in %, and the total number of garbage collections. A large number of collections or time spent in collectors usually indicates that the system is under memory pressure. Increase the amount of available memory to reduce the time to build the image. Now what this means is that, so what happens is the GraalVM, remember we're doing a static compilation, right? So it's not like when you run your Java application on the JVM, at runtime some garbage collection might happen to optimize the memory, to compactify the memory. But here we're doing a static compilation, so that if you allocate a byte array for the Java heap, right? But this array doesn't dynamically get optimized, right? So when you create your native binary and run it, this byte array might get fragmented because there is no GC. So what happens here is that behind the scenes, the static compiler actually runs through your Java application, and native image or the GraalVM has a GC. built in, and it actually runs the application, your Java application, and then runs a couple of GC cycles to optimize your image heap, right? So it's very interesting that this happens behind the scene, and this is one of the difficulties that they had to overcome to enable this kind of native native compilation, which is very interesting job to do. It's I'm sure it's not easy, but they were able to do it. So your native image compiler, in order to optimize your application, right, this image heap, which mimics the Java heap, we know that once you allocate and then objects and then they go out of the scope, your heap becomes fragmented, and it's the job of the garbage collector to reclaim those memory and also compactify the heap. So make all the live objects into put them one after another, so that the heap is very compactified. So it tells you, the compiler actually ran through your Java application. It ran 38 GC cycles to make sure that the image heap that it creates is mimicking a very compactified and optimized version of a Java heap, right? So 38 GC cycles were ran before the compiler decides that, okay, the state of the Java heap is the most optimized. Let's print it permanently as the image heap. Let's save it permanently as an image heap. And it becomes about 7 megabytes. All right, and then peak RSS, peak resident set size as reported by the operating system. This value indicates the maximum amount of memory consumed by the build process. Now, obviously, when you compile anything, you need some memory space, some RAM, so that the compiler can store some information, and eventually linker uses those information to build your binary. CPU load, and this is pretty much self-explanatory. The CPU time used by the process divided by the total process time increase the number of CPU threads to reduce the time. And by default, the native image tries to take advantage of all the threads that your CPU, the hardware, provides. So you don't need to pass any flags for changing the number of threads. I recommend you just use the default, whatever the number is for the default threads that the compiler uses. So let's go back to our Windows machine, and as you can see, the compilation has succeeded. We get myapp.exe. It tells us we're using the most recent version of the GraalVM compiler, 22.1. The C compiler, it was able to find cl.exe, which is the Microsoft Visual Studio compiler, and we use the 64-bit configuration, right? And this is the version of the compiler, 19.31. The garbage collector is serial GC. It's performing the analysis. It actually took 6 stars, so a lot of iterations to try to find all the classes that are all the methods, all the fields that are related to our Java application. Building universe, parsing methods, it takes 2 stars. If I go back to my Linux, you see on the Linux it took 1 star, but here it took 2 stars, so it tried to work a little bit harder. Inlining methods, and then compiling method, creating image here, it's actually larger, 12.54 megabyte, right? And it tells me about 4.7 megabyte is for code area, about 7 megabyte for image size, and it tells me it ran 19 GC cycles. Here, if you go back to PowerPoint on Linux, it actually ran 38 GC cycles. So on different platforms, it's going to be different. And then CPU load 1, right? And eventually we get our executable. So if I clear up and then I just say my_app.exe, I don't need to really type the exe. I'm going to do it. It's going to say hello world from C++ in Java. So we successfully compiled our simple hello world Java application into a native executable binary. So I hope you really enjoyed this lecture, and I'll see you in the next one.